Inference methods are techniques used in artificial intelligence to derive new conclusions from known facts and logical rules. These methods help machines make decisions and reason about the world. The most commonly used inference methods are resolution, forward chaining, and backward chaining. Each of these has its own way of reasoning, depending on how the information is structured and what the system is trying to achieve. Resolution is a method used mainly in propositional and first-order logic. It is based on the principle of refutation, where the system tries to prove something by showing that the opposite leads to a contradiction. In order to use resolution, all the logical statements must be converted into a format called conjunctive normal form, or CNF. This format involves breaking down complex sentences into simpler ones using only ands and ors. The resolution rule works by finding a pair of clauses where one contains a literal and the other contains its negation. When those two clauses are resolved, the result is a new clause that combines the remaining parts of the original clauses, excluding the complementary literals. If an empty clause is eventually produced, that means a contradiction has been found, and therefore the statement we were trying to prove must be true. Forward chaining is a reasoning method that starts with known facts and applies inference rules to discover new facts. It is called data-driven because it begins with the available data and keeps applying rules as long as new facts can be generated. The process continues until either the goal is reached or there are no more applicable rules. This method is especially useful in expert systems and rule-based engines, where the system needs to draw conclusions from a large base of known facts. Backward chaining works in the opposite way. It starts with a goal or hypothesis and tries to find facts that support it. It is goal-driven reasoning. The system looks for rules that can lead to the goal and then tries to prove each of the conditions or premises in those rules. If the premises themselves are not known, the system recursively tries to prove them too. The process continues until all required facts are verified or until it becomes clear that the goal cannot be supported. Backward chaining is commonly used in systems like Prolog and other logic programming environments. Let's go through a simple technical example to see how these methods work. Suppose we have the following knowledge base. First, if it is raining, then the ground is wet. Second, if the ground is wet and people are outside, then the park is empty. Third, we are told that it is raining. Fourth, we are told that people are outside. The goal is to determine whether the park is empty. Using forward chaining, we begin with the known facts. It is raining and people are outside. From the first rule, we infer that the ground is wet. Now that we know the ground is wet and that people are outside, we apply the second rule and conclude that the park is empty. So, by starting from the facts and chaining forward through the rules, we reached our goal. Using backward chaining, we start with the goal. Is the park empty? We look for a rule that can give us that conclusion. The second rule says the park is empty if the ground is wet and people are outside. So now we need to prove that the ground is wet and that people are outside. We already know people are outside from the given facts. To prove the ground is wet, we check if there is a rule for that. The first rule says the ground is wet if it is raining, and we know it is raining. So we can confirm that the ground is wet. Since both conditions are satisfied, we conclude that the park is empty. This is backward chaining in action. Now consider resolution. To use resolution, we need to express our knowledge in propositional logic and convert everything to conjunctive normal form. Suppose we want to prove that the park is empty. We assume the opposite, that the park is not empty. Then, we try to derive a contradiction using the known rules and facts expressed in CNF. If a contradiction is found, meaning that our assumption leads to an inconsistency, we conclude that the park must be empty after all. The process involves pairing clauses, resolving literals, and simplifying until either an empty clause appears or no further progress can be made. Each inference method has its strengths. Resolution is powerful for proving logical statements and is used in automated theorem proving. Forward chaining is efficient when we have lots of data and want to derive all possible outcomes. Backward chaining is ideal when we have a specific question and want to trace back the conditions that would support it. Together, these methods form the foundation of reasoning in artificial intelligence, enabling machines to make logical decisions, validate information, and solve complex problems by connecting dots between what is known and what can be logically inferred.